Hey, World Patriots. This is the math teacher to teach you math.
Wait, you're not the math teacher. Hey, I'm the math teacher. What are you doing over here? Are you trying to steal my channel? What? No? Okay. All right, here, you take that off. Let's go. Come on, it's my turn. Come on.
Okay. I'll tell you what to say.
Okay, no, for real. I am the math patriot. Sorry, my son got carried away there. He wanted to try and teach the lesson for some reason. I don't think he knows anything about tangents, but we're going to give this a shot and see if I know something about tangents today. Hopefully my mental math skills are working a whole lot better than last time. Some of my students were calling me out on that, and I was kind of just giving them some junk right back. But you know what? It's all good. We all make mistakes sometimes. We all have bad days. And I don't mind showing you guys that stuff because, you know what? I make mistakes too. The important part is that we just keep on going. We admit when we make a mistake and we fix it and we move on. Sometimes we have to use the tools like these fancy calculators to help us through the issues we have each day. And no big deal. Let's keep on moving on. Today we're going to talk about tangents. Now this is a different use of the word tangent than you are used to. I say used to. The one that we used back in the trigonometry unit. In trigonometry, our tangent was the ratio, it had to do with the sides. So if we had a right triangle, we had, and let's call this our angle theta. Here we have our opposite side, our adjacent side, and our hypotenuse. The tangent of theta is equal to the ratio of the opposite side divided by the adjacent side. And while that is one definition of the word tangent, it is actually a very, very good definition of the word tangent, and it is honestly the one you'll be using most often inside of math classes. That is not the definition of the word tangent we are going to be using today. Today we're talking about tangents of circles. Now, a tangent is a line in the same plane as a circle that intersects the circle in exactly one point. Okay, so if I came in here and I drew this line, that is not a tangent line. That's actually called a secant line because it touches at 2 points. So that one does not count. Also, if I had a line over here that never touched anywhere, that would also not be a tangent. That one's just a non-intersecting line. Now, the point of tangency is going to be this point right here, in this case, point A, the point at which the tangent line and the circle intersect. Now, if you have two circles that share a common tangent, that's where a line or segment that is tangent to two circles in the same plane. There are different variations on how that can happen. Like over here, we've got this one that goes in between these two, and the one that meets in the middle whenever two circles are tangent to each other. They have a common tangent line. Now, something I want you to think about is that a lot of students typically start thinking about gears and cogs and pulleys and that sort of stuff anytime that they start looking at these things. Think of like a bicycle chain. Anytime that you have a string or a flexible object that's wrapped around a circle, it's most likely going to leave things at a tangent. Also, whenever you think about, for example, whenever you are spinning something around in a circle, I mean, let's say you got a person sitting here with a bucket of water. That's a really, really bad bucket of water, but let's say there's water inside of there. And he starts swinging around and around and around. Whenever he lets go, let's say that he lets go right here, and he's going around this direction, it's going to fly off, and its initial velocity is going to be a tangent to that circle that was formed by his shoulder as the center, and then the edge of, or out here at his grip as the edge of the circle, this being the radius. He's going around and around, that thing will fly off, and then of course from there, after that tangent line, then parabolic motion, your normal gravity stuff is going to set in. Tangents occur all over the place. Okay, whenever I see this stuff, I'm thinking about a set of pulleys, a rope going around pulleys, those sort of things. You see these placed all the time in engineering. Tangents are a very big deal. Okay, so let's jump into our examples. Got 10 examples for you. I cut this lesson and stripped it out so that we could get this done as quickly as possible. That way we're not doing a full 30-minute lesson. Okay, example 1, draw the common tangents, and if no tangents exist, state no common tangents. This is going to be the same directions for the first 4, and just to make things easy, I went ahead and put these in the PowerPoint. That way my drawings don't mess you up. So there are going to be 2 common tangent lines here, and they exist right there. Now, notice we have 2 intersecting circles here. If I was to try and draw a tangent line that went through here, that's not going to work because while it is tangent to the large circle, it is a secant to the small circle. Okay, so those are our only two that we can draw. On example 2, two concentric circles. Okay, concentric circles means they have the exact same center, and in this case, different radii. Now, if I try to draw a tangent to this circle, it is going to completely miss the small circle. If I try to draw a tangent to the large circle, or to the small circle, then it's going to be a secant to the large. So, in this particular case, there are no common tangent lines between those two circles. That's when you have concentric circles, no common tangents. All right, let's draw our common tangents to our two non-intersecting circles. These are going to look very similar to the ones from example 1. Just boom, those two right there. And example 4, whenever we have two tangent circles, let's look at our tangent lines that are drawn here. Again, very similar to the ones we saw before, but there's also a third one. Do you see where that one is? It was actually shown in one of the previous examples a few slides back. It's actually the one that goes right through the point of tangency of the two circles. So the tangent line is tangent to both circles at the same point of tangency. So this one's got 3 of them. All right, Theorem 1010. In a plane, a line is tangent to a circle if and only if, important, that is a biconditional, it points both directions. The hypothesis implies the conclusion, and the conclusion also implies the hypothesis. I could take the converse and it would still be true. Okay, if and only if it is perpendicular to the radius drawn to the point of tangency. So here's what I mean. I got line L, point of tangency here is at point T. ST must be perpendicular to this tangent line. Then there's also the other direction around. Let's say that I draw a radius and then I draw a line that is at a right angle to the radius right here where the radius intersects the circle. That means that that line L must be a tangent line. Tangent implies right angle implies tangent. Both goes both directions. All right, so let's say that we have KL. It's a radius to circle K. We want to know whether LM is a tangent. Justify your answer. Now, what we're trying to do here is we got to know, is angle KLM, is it a right angle? Because if it is a right angle, then LM must be tangent. So then the question is, how do I test for a right angle? And if you're thinking in your head the converse of the Pythagorean theorem, then you're right. So what we have to do is we have to test the Pythagorean theorem. If this is a right angle, then this would be our A, B, and C value, C being the longest one, the hypotenuse. So we got to know, is 20 squared plus 21 squared equal to 29 squared? And yes, that is a question mark above my equal sign because I am testing whether it's equal to. I'm not stating that it is equal to. And this one, I hope nobody gets all over me for using my calculator on this one. Well, you know what? I'll do my mental math where I can. 20 squared, I know, is 400, plus 21 squared, I will be honest, I have no idea. And I lost my mouse. There it is. 21 squared is 441. And now let's try 29 squared. My mouse keeps disappearing on me. 29 squared is 841. Let's see, 400 plus 441 is 841 equals 841. And yes, since the left side equals the right side, that does check out. So yes, LM a tangent. So testing our right angles. All right, now example 6. We know that AB is tangent to circle C. Find X. Well, in this case, since it is tangent, we know that this is a right angle. Therefore, I can perform the Pythagorean theorem to find X. So x squared plus 8 squared equals 9 squared. So x squared equals 60. Let's try and write the right symbols here. X squared plus 64 equals 81. Let's subtract both of them, or subtract it from both sides. 81 minus 64 is going to be 17. And you see now I'm second guess that. Yeah, 17. And then take the square root of both sides. X equals the square root of 17. 17 is prime, does not reduce, therefore we're leaving it as square root of 17. All right, in the figure, IK is tangent, find X. This one is going to be a little bit different than the one before. Our three sides here, of course, A is going to be X, B is going to be 16, but here the distance from I to J is going to be X plus 8 because we've got to add in the radius plus the piece outside. That A is the piece of that line between the edge of the circle and point I. So the full thing is X plus 8. So let's go through and run our Pythagorean theorem. X squared plus 16 squared equals X plus 8 squared. Sorry, calculator, you are in the way. All right, let's go ahead and run 16 squared. I should know that, 256. X squared plus 256 equals, now X plus 8 squared, remember we have to actually FOIL that out. That's X plus 8 times X plus 8. When I do the FOIL method, I'm going to get X squared plus 16X plus 64. If you didn't follow that, let me just piece it out. X times X is X squared. X times 8 is plus 8X. Down here on bottom now we got, that calculator is just determined to be in the way. Somebody really ought to teach him where his stage blocking is. Okay, let's try this again. Oh, my calculation now in my screen. What is his problem? All right, let's try this whole thing over again so you can actually see it. Erase all that. See, I'm trying to make a short video and then I do stuff like this and I make it take up more time. So X plus 8 times X plus 8. X times X is X squared. X times 8 is plus 8X. 8 times X is plus 8X. And then X 8 times 8 is 64. Leaving me with X squared plus 16X plus 64. Okay. X squared plus 16X plus 64. Okay. Now we're going to, it looks like I got X squareds on both sides. I'm going to go ahead and subtract this X squared, meaning that those guys are going to cancel out. I'm going to leave the 16X here on the right, and I'm going to subtract 64 on both sides. That's going to leave me with 992. Now we're going to divide both sides by 16, leaving me with X. Stop disappearing on me. Are y'all seeing that disappear? X equals 192 divided by 16, 12. X equals 12. Okay, if two segments from the same exterior point are tangent to a circle, then they are congruent. Here we go. We got point B outside the circle. AB is tangent, CB is tangent. That means that these two, my pen didn't work. I'm having all sorts of technical difficulties today. These two are congruent because they are tangent to the circle from the same exterior point. All right, so here we go. Point C is an exterior point. AB is tangent, BC is tangent. Therefore, these two must be equal to each other. So 3x plus 2 is going to equal 4x minus 3. Yes, I know I wrote that weird, but I wanted the positive or the greater one to be on the left. So I went ahead and chose to put that over there. Subtract 3x gives me x. Add 3 gives me 5. And we are done. Okay. circumscribed polygons. When a polygon is circumscribed on a circle, all of the sides of the polygon are tangent to the circle. So in this particular case, every single segment there has a point of tangency. Okay, every single point all the way around has, or slide is a point of tangency. Therefore, the important part there is that since these are all tangent segments, then each of these are congruent. Now, in this particular case, they were both regular polygons, a regular hexagon and a regular quadrilateral or a square. That's not important, okay? That just happens to be the picture that I chose here. You'll see that in the next two examples. So, for example, find x and then find the perimeter. Notice this is not a square. It is just a quadrilateral. Now, I'm going to look at these two where the x is, and notice that this is a exterior point that is tangent to the circle. Therefore, these two equal each other. Therefore, x plus 2 is equal to 8. Subtracting 2 gives me x equals 6. Okay? Now, honestly, in this particular case, I don't need to know x in order to find the perimeter, because I could always say that if that segment is 8, then this segment is also 8. I mean, plug it in. 6 plus 2 is 8. Either way, it works. Okay. So, do that so we don't think it's a division bar. Okay, so then for our perimeter, it's just 8 plus 8 plus, now this is 5 and that is also 5. So 5 plus 5. Now if this is 9, then that is 9. Plus 9 plus 9 plus, then here's 4 and this is also 4. So it's 4 plus 4. So that's going to be 16 plus 10 plus 18 plus 8. So that gives me 16 plus 6 is 22. Carry the 2, 2, 3, 4, 5. So my perimeter is 52. And if I mess up that one, then my class is all going to razz on me really, really bad because I messed up on elementary school math. Hey, you know what? If we did, leave it in the comments and we'll all just pretend that I'm perfect in every possible way. I'm the Mary Poppins of mathematics. Okay. Number 10, last example of the day. Find x to the nearest hundredth. Okay, assume that all segments that appear to be tangent are tangent. So let's see what we've got here. If RS is tangent, then that means that this must be a right angle and this must be a right angle. Since this is a radius, QR is a radius, QT, which is also a radius, must also be 4. Now, let's see, that means this piece right here must also be 4. And, oh, that means QS, the entire distance is 9, because it's 4 plus 5. And then we're trying to find X. So that must mean that I have a right triangle here. My right triangle is happening at QTS. And my side lengths are 4, 9, and x. So I've got 4 squared plus 9 squared. Whoa, I'm sorry. 4 squared plus x squared equals 9 squared, because 9 is going to be the hypotenuse over on the right. So we got 16 plus x squared equals 81. X squared is equal to 81 minus 16, 65. And then x squared equals the square root of 65. And let's see, 65, how does that break down? That's going to be 5, and stop disappearing on me. I think it's this like general region of the screen, like right in here. It doesn't like to that's where all the mistakes seem to happen. So let's try this. 65 breaks down into 5 times 13, both prime, does not reduce anymore. Therefore, x equals the square root of 65. All right, that's all we've got for today. That's all of our tangent lines. Let's see, I said I wanted to keep it down to under 30 minutes, and we are right at 21 minutes. So that works. All right, so that's all we got for today. For my class, enjoy the assignment. Everybody else who is not in my class, have fun just learning math for the sake of learning math. Why are you here? I don't know. Anyway, everybody still got the coronavirus stuff going on. Please, everybody, stay safe, stay healthy. Don't touch other people. Distance yourself as much as possible, but please go to the store and buy toilet paper in necessary, appropriate amounts, and because that's the patriotic thing. Stay patriotic.